Hello everyone, welcome back to my channel. Today I will show you how to calculate some properties of water molecule. And I will focus on the two properties. One is the bond length, one is the bond angle. I have already written the reference here from the literature, and I will calculate them separately using quantum espresso. And we will compare our calculation with the literature and see how much is the error. Okay, so let's get started. I already sourced the Intel libraries, so everything is ready to be used. And I also already written the input file. Let's take a look. So the calculation type is still the same, is relax. We change the prefix to H2O. And I add two lines here. This is the total energy convergence threshold, and this is the force convergence threshold. Those two works for the relaxation calculation. So if you lower these two values, you will get more precise calculation. And usually if you don't specify this, like what I did last time, it is 1 minus 4 and 1 e minus 3, so it's less accurate. And we keep the Bravais lattice to be a simple cubic lattice, and lattice constant is 10. I reduce it to let the calculation more efficient. And there are 3 atoms in one unit cell because it's H2O molecule, and there are 2 types of atoms now: one hydrogen, one oxygen. And everything else here is the same, and we specify the atomic species, and this hydrogen and oxygen, and atomic mass, and the pseudopotential files that comes from the SSSP library. Yeah, and the atomic positions I still specified in angstrom because this is more clear. And for oxygen molecules it's around 000, and hydrogen molecules are around 1 angstrom apart. One is plus 1 in the x direction and -1 in the x direction. Notice that here you should perturb a little bit, let's say 0.01 or 0.02, to break the symmetry. If you write here as 0, 0, like -1, 0, 0, or 1, 0, 0 here, the quantum espresso program will detect a high symmetry, and it will only move those hydrogen atoms along the x direction, and it will not converge to the final shape that we want. Yeah? And the k points, we still keep it as only 1 k points. That is the gamma calculation. So let's get started. And so npi run minus np2 course, and the path to the quantum espresso p.x, and minus imp, and h2o in output to h2o out. Yes, and this will take some time. If you want to check the computation in real time, you can open a new terminal and go to the folder calculation 2 and write tail minus f h2o relax dot out. Yeah, and then it updates the output automatically. Okay, you see that it's dropped down. And so we can go inside the output file to see. So the final position is written here, and in this case it is not as easy as the last time because everything is in 3D, and of course you can still get the bond length and bond angle just from these numbers, but it's not very direct. So I will use the software called xCrystal that I mentioned before. So the full path to xCrystal is, I remember, something like that. And we just enter, and open pwxcf. This is the output and input for pw.x and output file. Yeah, we choose the relax.alt and do not reduce dimensionality and as an animation. And you see that it is like the hydrogen atoms are apart. That is because we have a periodic boundary condition. Yeah, so those are all oxygen atoms and those are hydrogen atoms. So in principle, it calculates something like that. It calculates some a big grid like that, and there are many hydrogen atoms inside. That's why we want to choose the unit cell to be very large, so that the hydrogen atoms are decoupled from each other. Yeah. So in this case, you may want to click here. So so it only draws one molecule in the unit cell. Okay, and you see that this is the starting point where it is everything is in one line, and you can click here, play forward, and this is the path of the relaxation. You see that it gradually converges to the final water molecule. Okay, so this is the result, and we want to measure the angle. Click here, angle, and like 1, 2, 3, and we click done, and it's around 101.112 degree. We copy it here. Okay, we cannot copy it, so it's 101.112 degree. And then we want to measure the distance in angstrom. This is 0.9994. 0.9994. Okay, so this is the result, and the bond length for the H2O molecule has an error around 4%, and the bond angle is around 3%. So this is quite accurate, I would say. Yeah. So in this video, I've shown you how to calculate the bond length and bond angle, and how to visualize the result in X crystal of water molecule. And I hope to see you next time.